Very good morning. I am J.H. Gabra before you to present my work on effect of innovative forms on MTHA, that is modal time history analysis for cable supported bridges against my conference ID 1232. I myself am working as head of applied mechanics department at Government Polytechnic Himmatnagar, and along with it I am a research scholar pursuing my PhD under the supervision and guidance of Dr. A.K. Desai from SVNIT, Surat, Gujarat, India. To talk on my topic on effect of innovative forms on MTHA for cable supported bridges, the outline as can be seen over here gives a brief about classification of bridges, need of the day for long span bridge, cable supported bridges, and innovation, problem statement on showing the effect on MTHA, followed by conclusion and some references. As can be well known, we can define a bridge very easily. It can be seen it's a structure built to span physical obstacles meant to provide passage over the obstacle without closing the way underneath, such as a body of water, valley, or road. Now, such structure is termed as a bridge. Going for a pictorial view on a brief of history of the bridge development, it can be seen it goes way back to 100 BC, where Romans built a Roman arch bridge. This was made of natural concrete made from mud and straw. On the right side, we can see a great stone bridge in China built in 700 AD, which allowed boats had a shallow arc and water to pass through. It's a low bridge. Talking of the 20th and 21st century, we can see some truss bridges pictured over there. Suspension bridge of 1920, followed by a pre-stressed concrete or steel bridge picture that was built in 2000. Now the classification of the bridges can be based on for the function for which it is built up, the material used for the construction of the bridge, the superstructure. Similarly, it can be classified based on the interspans or the bridge floor or the connection done. Now talking of the superstructure, beam, it can be a slab beam bridge, it can be a beam bridge, truss bridge, arc bridge, or it may be a cable supported bridge. Over here we can see two forms of cable supported bridges, that is suspension bridge and your cable stayed bridge. Now the question arises, why do we need exactly, what is the need of the day? Long to super long spans. Why? Now it can be seen that due to increased traffic because of globalization, competition, it is seen that greater horizontal clearances for navigation owing to increased size of vessels has thwarted upon the need of long to super long spans. This has an economic impact too, because it may result in reduced failure of the bridge due to vessel pier collision, as there will be less piers if we have long span to super long span bridges. Now this may also result in minimized number of piers, leading to less foundation excavation and relocation thereon. So it all combines together, all these factors add and put in a much needed need of the day, that is provision of long to super long span for the bridges. Now if we talk of specifically of cable supported bridges, the innovative forms available are in form of suspension bridge, cable stayed bridge, or a bridge with hybrid cable system. Now if we talk of suspension type of bridge, we can be seen that this is the girder on which the traffic is there. This load is transferred from this girder to this vertical cable or hangers. Now these are supported by this catenary or suspension cable. So it is very much clear that the load is transferred. Mechanism is simple. Load is transferred from this girder to this hangers to this suspension cable. Now from the suspension cable either to this tower, that is pylon tower, back to ground, or in form of these anchorages. So this is a case of a suspension bridge. Now it can be seen number of suspension bridges are available in the world. For example, Akashi Kaikyo Bridge, which was built in 1998, has a span of 1991 meters. Same way, Aski Bridge of Norway is 850 meters. It was built in 1992. So in last 50 years, a variety of bridges ranging from more than 800 to thousands of meters built all across the world. Now, second comes the cable stayed bridge. Now, if we go for cable stayed bridge, the arrangement is like this. You have a girder, the load is transferred, it is supported on these cables. Now these cables take the load from the girder, get it transferred to this pylon top, from pylon it comes back to the ground. So this is your cable stayed bridges. So the longest bridge in the world is definitely the Ruski Bridge of Russia, is a cable stayed bridge which spans to about 1104 meters, and it was completed in 2012. And after that too, various bridges have been formed in China too, where the cable stay portion is there. So it can be seen that cable stay bridge is much more rigid as compared to the flexible suspension bridge. The third type can be seen is hybrid bridges having hybrid cable system. Now when hybrid comes, it's a combination. It's a composite or it can be combined one. So when it is a composite, you have on either of the suspension bridge or CSBs partly having on the bridge, whereas in combined you have a combination of both systems. Now cable stayed suspension hybrid, that is CSSHB, it can be in form of two ways. Either you have hybridity in form of materials used, that means deck may be a portion of deck may be of steel and remaining portion may be of concrete too, whereas over here I am talking about the cable patterns only. So it will have either no overlap of suspension or hybrid bridges or cable stayed bridges, or it may have some partial overlap. So which we can see over here in this figure. Now this is a cable stayed suspension bridge. Now in this central portion is a suspension portion. Over here you can see it's a cable stayed portion. So it's a combination of suspension as well as cable stayed bridge. Now over here you don't have any overlap. So this is a case of CSSHB, that is cable stayed suspension hybrid bridge with no overlap between suspension and cable stayed portion. The mechanism is the same. This load is carried by this either vertical hangers or this cable stays back to this column pylon tower back to ground, or in form of these anchorages. So that was the cable stay. Now this is one of the problems which I am considering over here. The bridge is similar to that of East Channel of Lingding Strait in China. The bridge configuration is like this. It's a cable stayed suspension hybrid bridge in which suspension portion is approximately 612 meters. The side span is 319 meters. Main span total is 1400. Height of the pylon tower is 258.986. The cable sag to span ratio is 1.1:10. That means if this is 1400, the sag, maximum sag at the center is 1400 by 10, that is 140 meters. So this minimum length of this stray again will be some approximately 100 meters over here. 100 meters over here. Now the material used for using the model or manufacturing model is shown over here. It's made of steel of Fe345 grade and concrete M25. Now I prepared this models using SAP 2000 software. In this software, the various elements, girder is modeled as spine. Is the frame elements using steel as material with thin plate enclosures. It's a steam streamlined bridge. You can see over here, the picture shows over here. This is a girder, is approximately 38.6 meters long, and this is approximately 8 meters deep. The area is 1.792. This is the model extrusion over there. This is the cross section. Same way, the pylon is H-type, door type tower. in which it is modeled as a frame element using concrete as material with 6 meter by 5 meter in cross section and 258.986 meters precisely high. It has 3 transverse beams across its height, which can be seen over here. You can see this yellow portion is extruded form of pylon tower. This blue color is regarding your transverse beam. The cross section can be seen. These are solid concrete sections, 6 by 5 and 4 by 2.5, made up of M45 concrete. The cables are modeled as cable elements. There are a number of cables which range from, depending on the position, the diameter of the cable stays is ranging from diameter of 0.09 meters, 0.635 to 0.109 to 0.1354, whereas the hanger and main cable do have different diameters depending on their position, depending on the need of the force or the stresses. They are made up of Fe345 grade, so they have been designed accordingly. The supports and links are modeled as in accordance. So the innovative modifications which I am doing is I have the model 6 models: type 1, type 2, type 3, type 4, type 5 and type 6 type of bridge. Now type 1 is the original one, similar to the original, that is CSSHB, which is a leading straight bridge. It is a cable straight suspension hybrid bridge, in which we have seen the detail. The type 2 is SB, that is suspension bridge, in which I have converted this complete SSHB into suspension bridge. The hangers and are having the same what it was with the diameter parameters or the properties of the hangers and cables is the same as that it was in the original CSHB. Type 3 corresponds to CSB, that is cable straight bridge, in which this type 1 has been converted purely into cable straight bridge. Type 4 and 5 are composite parts, in which in type 4 you have the side spans as cable supported and inner span as central span as suspension bridge, whereas in type 5 it's a reverse one, in which side spans are suspended type and central span is cable straight. The type 6 is combination of type 2 and type 3. Now this can be seen over here. You can see this is the original CSHB type 1, in which it is a cable straight suspension hybrid bridge with no overlap. Type 2, I have converted this into a suspension bridge only. Type 3, you can see it's pure cable straight. Type 4, a composite form, central is cable, side is suspension. Type 5, side is cable, center is suspension. Type 6, combination of this 1 and 2 and 3. Loadings. You can see, loadings have been shown as in the table: dead load, live load, and a side imposed dead load. I performed MTHA using time history of Bhuj earthquake, January 30, 2000, magnitude of 7.7 Richter scale, duration of approximately 2 minutes, with a PGA of 1.03, 8 meter per second square. Performing the analysis, the model time history analysis yielded this what is shown on over here: tabulation form of time periods of all these 6 bridges up to 7 modes, and the same has been represented in form of pictorial graph. You can see it is following almost the same pattern. Almost the same pattern is over there, except these two. So while we conclude, I can state the trend observed in the deviation in model time is almost same for all the cases. Type 6 bridge gives maximum modal period. Thereby, flexibility has increased by approximately 6.16%, whereas in case of third and fourth mode, lower time period for all types when compared to type 1. So more rigidity is there. Time period for 7th mode for type 6, that is combination of type 2 and 3, it is higher than the type 1. Type 1 is your original cable straight bridge. This is all what I wanted to present. This follows a slide of references for you. Thank you very much. Bye-bye.